So without further ado, we'll switch over the computers. Tim, do you want to?
Good morning, everybody. Welcome back.
Excellent.
No governmental delays this week. No snow on the ground, no football game delays. Anyway, so this is the beginning of our series for 2018, and it's my great pleasure to introduce Dr. Sleeman Benjamaya. He's come to us from the University of Chicago. Give a little bit of his. He's asked me to be brief, so I will be. He got his undergraduate degree in cognitive science from the University of Virginia. He popped down one state from there to North Carolina, where at the University of North Carolina he was in cognitive psychology for his PhD with Mark Collins. From there he went back up the East Coast to Maryland and Baltimore, where he was at the Krieger Institute,
Mind Brain Institute, yep.
And then joined the faculty at the University of Chicago in their organismal biology and anatomy program. He's also a member of their neuroscience, or their neurocomputation group and neurobiology. He is a leading expert in somatosensation and neural encoding of that sensation. He combines electrophysiology, neurophysiology with psychophysics, computational neuroscience. I think the first time that I had the opportunity to meet him, he was engaged in a provocative conversation. You'll often find Sleeman involved in provocative conversations about the role of electrical stimulation in reanimating the damaged nervous system. The issue there was whether or not it was important that the simulated stimulation represent what we normally find encoded by sensory systems, or was just any old sort of garden variety of electrical stimulation good enough? It was a very spicy conversation. Anyway, without further ado, we welcome you here, and we're excited to hear about biology of bionic.
Well, thanks for stealing my thunder. I guess I'm just not even going to give my talk now. You just said everything I had to say. So before I get started, thanks for having me. Really happy to be here for a variety of reasons, one of which is a thermal reason. It's much warmer here, so thanks for inviting me now. I think this was actually scheduled that way so I could enjoy the weather here. Before I get started on what I'm actually going to talk about, let me give you a little bit of background on what we do in the lab, which I think is going to sort of shape, the neural engineering I'm going to be talking about later. And what we do falls under the rubric neural coding. I'm going to be talking about touch, so I'll use that as an example. The idea is when you grasp an object, there's a spatiotemporal pattern of deformation produced in the skin, which I'm sort of represented with a squiggly line. And that creates and that pattern of deformation depends on what you touch and how you touch it. And it produces a pattern of activation in the nerve, which is going to then culminate in a pattern of activation in the central nervous system at different stages. In the cuneate nucleus, then in the thalamus, and then at various stages of processing in cortex, ultimately culminating in a percept of the object. And when we hold this object in our hand, we have information about its size, its shape, its texture. If it's moving across the skin, we have information about that too. And somehow, all that information is encoded in these patterns of neural activation. And what we spend most of our time doing is figuring out what aspect of this pattern of activation in the nerve and in the brain conveys information about texture, what aspect conveys information about motion, what aspect conveys information about shape. And we create these mathematical models where we can then, if you give me two patterns of nerve activation, I can tell you a lot about what caused them. I can tell you which of these two had the rougher texture. I can tell you what the shape of the grasp object was, whether it was moving, and if it was moving in what direction, at what speed. So we try to come up with these models that link not just the stimulus to the evoked response, but also to the percept that is ultimately elicited. That's not what I'm going to talk about today, but it sort of frames what I'm going to talk about today. Instead, I'm going to talk about how we can leverage what we've learned about how the intact nervous system encodes information, like how your nervous systems encode information about objects grasped in the hand, to restore that information to patients who have lost it. And we focus on two populations of patients. One are amputees. So they've lost their sense of touch because they've lost their arm, right? And I'm sure most of you have seen stuff like this around, where one strategy is to replace the function of the lost arm with a bionic hand that they can control, volitionally, usually through via signals from the residual muscles. But as I will show you in a few minutes, these hands are not going to be clinically viable, sort of useful things. They're pretty cool looking, and they do cool looking stuff, but they're not going to be useful until you restore the sense of touch, because really anytime you use your hand, not only are you moving your hands, but you're getting this barrage of signals back from your hands that is critical to using them. And so one strategy to restoring, or the strategy really to restore touch in these patients is to interface with an electrical interface with a peripheral nerve. So the nerve that used to innervate the hand is still there, right? So what we can do to create sensory percepts is to stick some electrodes in that nerve chronically, and there's a variety of different technologies that I won't get into. And then it's been shown many times now that if you electrically stimulate this nerve, you can create sensations that are projected to the hand. And if you electrically stimulate this nerve in intelligent and sort of informed ways, informed by what we know about how this nerve encodes information, you can actually convey very specific and quasi-natural sensations. That too is not what I'm going to talk about today, although I'm happy to take questions about it later. Instead, what we'll be focusing on is another population of subjects, tetraplegic patients. So these are people usually with a upper spinal cord injury who are paralyzed and insensate from the neck down. And for these patients, you can interface with the nerve because it's no longer attached to the brain. So you can stimulate the nerve if you want. It's not going to evoke any sensation. And so with these patients, because the nerve is no longer connected to the brain, you have to interface directly with the central nervous system. There's a variety of different places you could stick your electrodes. The cuneate nucleus, we're looking into that, but it's very difficult because it's in the brainstem and near a lot of vital functions. The thalamus, which is hard to access and hasn't really been taken seriously yet. And the most accessible place is the primary somatosensory cortex, which sits right there on the surface of the brain. And so that's what I will be talking about. So the idea is to restore, so these patients too are equipped with bionic hands that they control with thought alone, and I'll show you that in a minute. But the idea is to convey that sensory feedback by electrically stimulating their brain directly. But before I go into all that, I need to kind of try, because most of you haven't really thought about this, I assume, try to explain to you why you would go through all this trouble to restore the sense of touch. So this is a movie I made of me doing a bunch of stuff with my hands. Most of it mundane stuff that you do on a daily basis, like picking up things, writing with a utensil, typing on a keyboard. And these are things that I could not do without the sense of touch. Because again, anytime you interact with objects, you get these continuous signals coming back from your hand that inform you as to the consequences of these movements. And without these signals, you would suck at using your hands. You don't have to take my word for it. I'm going to prove it to you. This movie was made by a colleague of mine at Umeå University, Roland Johansson, of a lady lighting a match. Moments later, same lady is doing the same thing. The only difference is her fingertips have been numbed with a little bit of lidocaine. And now if you look at this, it's kind of excruciating because this simple task, this thing she could do effortlessly moments earlier, now she struggles to do. Like that, she drops a match. She can see this match. She's neurologically intact. She's sober. She can see the match. She just realizes she's not going to be able to pick it up without these tactile signals. And eventually, she picks up the match and lights it. And she's never going to get better at this. Half an hour later, she's still struggling to light matches, right? And again, sort of illustrating. And so again, her motor system is intact. Most of her somatosensory system is intact. The only thing is her fingertips has been numbed, and she struggles to do this task. Now, this next guy is doing something even easier than lighting a match. He's just trying to pick up this coffee cup and bring it to his mouth. Now, he has suffered from a rare peripheral neuropathy that has left his motor system intact, but destroyed all somatosensory signals from his hand. So all touch, all proprioception gone. And now, he struggles to do this even simpler task of grabbing this cup and bringing it to his mouth. even though his motor system is intact. And if I showed you this guy and you didn't know anything about him and I said, what do you think is wrong with him? You would think he has a major motor impairment, right? And that illustrates the yin and yang between somatosensory system and motor systems. And the motor system basically cannot work without the somatosensory system. So that's true of your bodies, your intact bodies. If I take away from your somatosensory system, you are going to struggle to do anything with your body. Now imagine now in this case. So this is Jan. She's a tetraplegic patient who has been equipped with an array, with a pretty cool anthropomorphic robotic arm. And she controls this arm via an array of electrodes that have been placed in the primary motor cortex. So this is the part of the brain that sends signals to the muscles. And my colleagues at Pitt, and they're one of many groups that have done this, can infer intended movements from the patterns of neural activation in this part of the brain. The idea is anytime you move your arm in a specific way, that is predicated upon a specific pattern of activation in this part of the brain. And they have models, and they're relatively simple models that sort of do a mapping between patterns of activation in motor cortex and desired movements. And then they implement these desired movements in these arms. If all this was word salad, the take-home message is she just thinks about moving her arm and boom, there goes the robot. And she can basically control this robot by thought. So if you're seeing this movie for the first time, you're like, whoa, that's pretty cool. What a great, amazing scientific and technological achievement. This person can control this relatively complex robot just by thinking, right? If you see it for the 100th or 1000th time, you're like, man, I'd be way better at this than she is. You'd be like, woof, woof, woof. But she's about as good as you would be if you didn't have a somatosensory system. If you see the last guy I showed you, if he was doing this task, he too would struggle. He too would be super slow. And so the idea is, if you want to create a bionic hand that is endowed with the dexterity that we are endowed with our hands, you would need not only to restore the motor system, but you also need to restore the somatosensory system. And what I'll focus on in this talk is our efforts to restore the sense of touch. I'm showing this movie because I think it's cool. I in no way am endorsing this remake of RoboCop. But if you want to play guitar with prosthetic hands, you're going to need a sense of touch. And we're there for you. So this is just a little animation to kind of give you a sense of how this works. So the idea is, anytime you touch something, your skin deforms, and it creates a pattern of activation in receptors in your skin that depends on what you touch and you touch it. These receptors send signals to your brain via the nerves, and culminate in a pattern of activation in the somatosensory cortex. So this is the part of the brain that receives input from the hand. And that pattern of activation depends on what you touch and how you touch it. These prosthetic hands have sensors in them that replace the receptors in the hand. And our goal is to create algorithms to convert the output of these sensors in real time into patterns of stimulation of the brain to recreate, to the extent that we can, these natural patterns of stimulation, which I told you, I started this whole talk by telling you, that's what we spend most of our time doing, is how does this part of the brain respond during interactions with objects? So this whole thing started as a DARPA program, and I mention this because, well, DARPA is very goal-oriented, right? They're like, okay, you have 2 years, you have 2 years to do 5 years worth of work, and at the end of these 2 years, what we need is an algorithm that converts the output of sensors into patterns of electrical stimulation of the brain, right? It's not like, hey, here's some money, just do some cool stuff with it and let us know what you discover. And so because of that, you sort of have to find a problem that is tractable, right? And so, rather than trying to restore touch in all of its glory, which is, we don't completely understand really the central basis of touch in the first place. And second of all, even if we did, we could not just figure out how to restore it in 2 years. We decided to focus this analysis, or focus this project, on the necessary information to grasp an object, right? We wanted to endow the patient with the ability to grasp and pick up an object. So what kind of sensory information do you need for that? Well, you need to know that you're touching the object, right? You need to know where you're touching the object. Minimally, you need your thumb and one of the fingers to be touching the object if you hope to pick it up. And you need to know how much pressure you're exerting on the object. You want to exert enough pressure so as to pick it up, but not so much pressure as to crush it or just even strain on it unnecessarily. So we wanted to focus on these 2 dimensions of touch: contact location, where are you touching the object, and contact pressure, how much pressure are you exerting on it. And this, we're super good at these things. We know, obviously, when we're touching something, and we know we just exert just enough pressure on things to pick them up and no more, right? And that's thanks to our sense of touch. So we wanted to convey these through this brain interface. This little arrow is to remind me that I am kind of a big believer, and I will defend this today if you challenge me, and I'm happy to be wrong, but I doubt I am on this particular point, that what we try to do is we try to reproduce natural patterns of activation in the brain. And if you have never thought about sensory feedback in brain-machine interfaces, you're like, well, duh, is there another way, right? The other way is to say, you know what, man, the brain, it's like a plastic thing. It'll learn. Just give it a new pattern of activation. It'll figure it out in time, right? And there's some experiments, I won't single anyone out in particular, that show that, yeah, you can learn new sensory spaces in, a few weeks or a few months. But they're very simple sensory spaces, like 2 dimensions tops. No one has been able to do anything beyond 2 dimensions. The issue with this, the brain is plastic hypothesis, is that the hand is super complex. The hand and the arm together have many, many degrees of freedom. They can move in a bunch of different directions. And the space of all the possible contact events is basically, for all intents and purposes, infinite, right? So imagine now that you're a tetraplegic patient, and I'm sticking an electrode in your brain to restore your sense of touch. And I've done this kind of plasticity-based approach. And now, basically, this means that anytime you you wiggle your prosthetic thumb, you're going to get this one tingling sensation. And you touch something with your index finger, you get another tingling sensation. And you have to keep track of all these completely nonsensical tingling sensations and hope that eventually they'll all make sense. It's possible that they will all make sense. I think it's very unlikely that in adulthood, without the benefit of sort of these evolutionary circuits that have been sculpted through hundreds of millions of years, and without the benefit of this massive plasticity that we have in childhood, that you can learn these kinds of representations. And so I don't think it's possible. But even if it were possible, it would be way better if these sensory prostheses were plug and play. You do this thing, and immediately all this sensory feedback is completely interpretable, right? Now, it's obviously not going to be completely natural, at least not anytime soon, not as long as we're still using electrical interfaces. But to the extent that we can sort of approximate these we can tap into these natural representation, and we can therefore approximate these natural sensations, these patients will have less to learn, and therefore will be able to use these faster and more effectively. So that's my position. And I put it out as a challenge to anyone to prove me wrong. And we wrote a paper, by the way, if you're interested in, because some of you might have read some of the literature on what happens after amputation, and you're like, whoa, staggering plasticity. Not at all. We wrote a paper about it. It was published in Trends in Cognitive Science in 2017. Check it out. Okay. Now that I'm going to get down from my soapbox and get back to the science bit. So I told you that the decoding happens by interfacing with the motor parts of the brain. Well, there's a part, the somatosensory cortex is the part of the brain that receives input from the body, the somatosensory input from the body. And as everyone in this room knows, within this part of the brain, there is a whole map of the body. In fact, there are 4 maps of the body because there are 4 cortical modules, one in area 3A, one in area 3B, one in area 1, and one in area 2. And within these body maps, so that means that depending on what part of your body you're moving or you're touching something with, a different part of this map is going to become activated. Within this map, you have a hand representation. So anytime you touch anything with your hand, this is the part of the brain that lights up. And even within this hand representation, you have this beautiful digit representation where D1 is always anterior and lateral to D2, which is always anterior and lateral to D3, et cetera. And this is the part of the brain we're going to target. we use basically right now we're still using pretty standard technology for this. So we use the Utah electrode array, which is basically the industry standard that I'm sure most of you have seen. It's 100 electrodes arrayed over a 4 by 4 millimeter area. And this is a nice electrode array because it has really dense electrodes, and also because we can use it in humans, as I will show you later. But the problem with this array is that really the electrodes can only be 1.5 millimeters long. And some of these structures that we're targeting are deeper than that. So for those, we use floating microelectrode arrays that are sparser but can have arbitrary long electrodes. And we use these to target area 3B. So we stick these electrodes in the brain. And by the way, this is work. First, I'm going to talk about work we did in monkeys. And then I'll tell you how we can apply these same ideas to humans. So we implant these electrodes in the monkeys. We let them recover for a week or so. And when they're recovered, we can map out these electrodes, right? So basically, the first way we do it is the easy way, which is you listen to the output of a given electrode, and then you palpate the body and figure out where you need to touch the monkey to evoke activity in this electrode. By the way, for those who are curious and are kind of somatosensory nerves, this is the nerds, this is the central sulcus, this is the intraparietal sulcus. The way we know and we have been able to consistently put our electrodes in the right place is that this is the face representation where the IPS ends, curls back towards the central sulcus and ends. This is the face, and therefore the hand is right, posterior and medial to that, along the central sulcus. Okay, so we have our electrodes in the brain. And now, whoops, daisy. Then we can map out what these electrodes respond to. So these guys here, for instance, this is this UEA. These guys respond to the palm. These guys respond to the index finger. These guys respond to the index finger. These guys respond to the middle finger. These guys respond to the index finger. I'm just kind of showing you in sort of very hand-wavy way this map of the hand that I'm telling you exists in primary somatosensory cortex. I'll show it to you in a more objective way later. So that's our interface. This is how we're going. This is the part of the brain we're going to interface with, and this is the electrical interface. Now, if we were doing these experiments in humans, things would have. If we had done these experiments in humans to start with, this would have been easier in some ways. Working with human tetraplegic patients is very difficult. I'm reminded by my PIT colleagues to tell people when I give this talk. But the nice thing about humans is that they have language. And perception is this internal thing, right? So in a human, you could ask, hey, you could stimulate the brain and say, hey, what did that feel like? Where did you feel it? Or tell them, this is the task that I want you to do with these electrical stimuli. And boom, they would do it. And boom, you get a high impact paper. With monkeys, though, well, first of all, they won't let you do that in humans in America until you prove that it's something useful. And then they'll let you do it. So we had to do for our first series of experiments in monkeys, and the situation there is we have to infer something about what the monkeys feel when we electrically stimulate the brain, right? So this is the strategy we took. So this is a monkey. He doesn't have this is not a mohawk. This is the electrode. So the lead's coming back from his electrodes. And the strategy we took is we trained these animals to do discrimination tasks where we poke their hands with this robot we designed that allows us to poke the hand anywhere with micron precision. And then we had the animals do a discrimination task based on these pokes, which I'll describe in more detail later. Once the animals were trained, we started replacing some of these pokes with electrical stimuli targeting certain structures in primary somatosensory cortex. And to the extent that the animal behaved as if it had been poked a specific way, we could infer something about what the animal felt. Right? That's our general strategy. And again, I'll go into more details. For those into ICMS, our electrical pulse trains are 300 hertz symmetric biphasic pulse trains shown here. Our mechanical stimuli and everything I'll show are just simple mechanical stimuli. And we've done other stuff since, and I'm happy to talk about it. But the basic stuff is just like these indentations into the skin. Okay. So I told you we were going to talk about contact location and contact pressure. And we were going to take a biomimetic approach. So the first question is, how is it that the brain tracks where we touch things, right? So I showed you, so this is the more objective way to sort of map out the hand representation in somatosensory cortex. So this is the neural activity evoked over this UEA when we poke the second palmar whorl. This is, so you can see it's sort of hot, so blue means not active, red means super active, and yellow means something in between. So the activity peaks here when you poke here with a mechanical stimulus. When you poke here with a mechanical stimulus, you get or you get a neural activation that peaks here. And when you poke the pinky, you get neural activation that peaks there, right? So again, I'm saying this now for the third time. You have a map of the hand in the brain. And so the hypothesis that we wanted to test, this biomimetic approach, right, was if we electrically stimulate neurons that respond to the index finger, will we evoke a sensation that is localized to the index finger? And really, not just to the index finger, but if we electrically stimulate index finger tip neurons, can we get a stimulus that is or a sensation that is entirely localized to the index finger tip, right? So again, this would have been easy in humans because we would have stimulated and they would have reported the location of the sensory experience. But instead, we were working with monkeys, so this is how we inferred where they felt things. We trained them to do a task where we might poke them on one location of the finger, in this case the ring finger of the left hand, and then poke them on another location of the hand that was radially displaced, in this case the middle finger of the left hand. And the animal's task was to say, was the second poke to the left or the right of the first? In this case, the second poke was to the left. After 6 tedious months, the animals figured out what it is we were asking, right? If it's a one pair, they figure out after a few days. But the ability to generalize anywhere, any pair of locations on the hand takes them a long time. But eventually, you can now take 2 random locations on the hand, and they can report which of the 2 locations, or whether the second location was to the left or the right of the first. Once we had trained them to do this mechanical task, and their performance stopped improving, we started doing the following task, where we might poke, say, the animal on the ring finger, on the middle finger, and then electrically stimulate it through an electrode that we had established had a receptive field on the ring finger. And the correct answer in this case was right? And to the extent that the animal would consistently or the animal's response matched the predicted response given the relative location of the poke and the receptive field location, we could infer something about what the animal felt, or where the animal felt it, rather. Important methodological point. To avoid that the animals might learn, oh, you know, if I feel a touch on my index finger and I feel some kind of weird tingling sensation, I have been rewarded to go left every time, so I should go left. And then, you know, rather than learning these stimulus response contingencies that had nothing to do with location, we wanted to, had on any given electrical block a bunch of different skin locations and a bunch of different electrodes. So the animal had no chance to learn anything about the specific stimulus response contingencies. The only way the animal could do this task is by judging the relative location of the 2 sensations, the mechanically and electrically induced ones. And one block, it was one set of conditions, and the next block, it was a completely different set of conditions. So none of that would transfer from one block to the next. And in other words, the animal had to judge the relative location, right? So it worked. That's why I'm talking about it right now. This is the mechanical, the performance on the mechanical trials, and you can see on some trials the animal did relatively poorly. So each of these points corresponds to a specific a pair of locations. So some of these pairs evoked poor performance when they were close by, right? Other pairs evoked near perfect performance when they were far away, right? So so this is this is sort of the baseline of when both stimuli are mechanical. When we replace one of the mechanical stimuli with an electrical stimulus applied to area 3B, which is really primary somatosensory cortex proper, we found that the performance was nearly identical to that. It was actually significantly less, but only because we could do a paired t-test because we matched the locations of the mechanical pairs and the hybrid pairs. But really, performance was very similar for area 3B. And then for area 1, it was less, significantly less than area 3B, but still well above chance, which if you know anything about somatosensory cortex, this would not come as a surprise to you because area 3B is primary somatosensory cortex proper, has small receptive fields, and area 1 is basically one synapse away from that, has larger receptive fields, so it's not surprising that the sensations evoked by area 1 stimulation would be sort of more diffuse than those evoked by area 3B stimulation. Regardless, though, in both areas, we found that the animals were well above chance, which can only mean one thing, and that is that electrical stimulation of primary somatosensory cortex evokes these highly spatially localized sensations. And I should mention, because you might be wondering, if you distrust me, which you should, that the animals never got better on the hybrid task. So we got them as far as we could with the mechanical task. And then when we started replacing mechanical stimuli with electrical stimuli, they were good and they remained good and they never got any better. So it's not like they were learning anything new with when we started the electrical stimulation trials. Okay. The other thing I said we were going to do is try to convey information about contact pressure, which is a little bit less straightforward. So if you touch something lightly or something touches you lightly with a low pressure, you get this faint sensation. If you jam your fingers on something or something is jammed against your skin, you get this much stronger sensation. What does the brain do, right? What is the neural correlate of that? Well, what happens when you touch something lightly is you have this faint activity that is highly localized. And as you increase the pressure exerted on the skin, you get an increase in the firing rate of neurons right there in the hot zone of activation, right, as shown here. And you get an increase in the volume of activated neurons, as shown here, right? I mean, you can see it in these plots, and this is across all skin locations. Both of these phenomena happen. So we're like, well, okay, if we want to convey information about pressure, we're going to do both of those things. We're going to increase the neural activation of the neurons near, in the hot zone, and we're going to increase the volume of activated neurons. We're going to recruit more neurons. The nice thing about that is we can basically do that, something like qualitatively like that, by just turning up the juice. I mean, the electrical current, right? If you have a weak current, you're going to weakly activate neurons just near the electrode, and that's it. As you increase the juice, you're going to more strongly activate neurons near the electrode, and the current is going to spread out and recruit more neurons, right? Okay, so that's our idea, but now we have to test it. We have to test the sensory correlates of increasing the juice. So we have to train these animals to do another task. In fact, we train them to do two very similar tasks, which is this is standard two alternative force choice psychophysics, where first we teach them to do a detection task. So in this case, first with mechanical stimuli applied to the skin. So here there are two intervals, like interval 1, interval 2, that are indicated by a visual stimulus. In one of those intervals, a stimulus, an indentation is presented, a very weak indentation, ranging from a 1/20th of a millimeter to a 1/3 of a millimeter-ish. And the animal has to judge which of these two intervals contain the stimulus, right? So they respond one way if it's interval 1, respond another way if it's interval 2. Then we had another version of this task, which is really a pressure discrimination task, which now we're indenting the skin twice on each trial. One indentation is a standard stimulus of constant amplitude. One is a comparison stimulus whose amplitude changes from trial to trial. This is a method of constant stimuli for the psychophysics nerds. So we used 5 or 6 different values for this comparison stimulus. 1, 2, 3, 4, 5. 5 different values for this comparison stimulus, and the animal had to judge which of these two was more intense. By the way, I talk about pressure, and then I give you microns so you're like confused because those are not pressure units. Those are units of indentation depth, which is monotonically related to pressure, as I will show you later. Okay, so we have so there's the low standard condition, and then there's a high standard condition where a 2 millimeter indentation is paired with these variable comparisons, right? And all these conditions are all mixed together, forcing the animal to really pay attention to both intervals in order to get the answer. Okay, so this is really standard psychophysics. And this is what the data look like. So this is proportion correct as a function of amplitude. I'm going through all this because it's going to become important later. I promise I'm not boring you for the sake of boring you. This is the proportion of times the animal correctly identified which interval the stimulus was presented in the detection task as a function of the amplitude of the stimulus. And of course, as the amplitude increases, it becomes more and more detectable, and the animal is more easily identifies which interval it was contained in. This is the mechanical pressure discrimination data, where this is the proportion of times the animal selected the comparison as being more intense, and as the the proportion of times the animal correctly identified which of the two stimuli was more intense, as a function of the amplitude of the comparison stimulus. And the reason why this goes up is because as the comparison amplitude increases, it becomes more and more different from the standard amplitude, and therefore that task becomes easier. In this case, it goes down because as the comparison amplitude increases, it becomes more similar to the standard stimulus, and therefore the task becomes easier, right? Or more difficult, I'm sorry. Okay. And then we did the exact same experiment with electrical stimulation of the brain, right? So now the detection performance, obviously it becomes more detectable if you turn up the juice. Discrimination, then we went a little cray-cray and tested all kinds of other parameters, like the effective pulse width on detectability, the effective frequency on detectability. So pulse width is completely predictable. Frequency, as you increase the frequency, detectability improves up to a point and then plateaus. Duration, again, increasing the duration improves performance and then plateaus. And anyways, and I'll tell you why we did all this in a minute. Well, I guess the big picture is this is a new sensory modality, right? We're trying to figure out how the detectability of these stimuli are dependent on the various parameters of the stimulus, as you would any other sensory modality. This is what the discrimination data look like. So you have, for the low standard, you have a upward going psychometric function. For the high standard, you have a downward going one, just like we saw for the mechanical stimuli. There's no effective frequency. There is an effective duration up to a point. So again, we wanted to characterize how this sensory space depends on the stimulus, stimulation parameters. This is why this was useful. It was really boring. I'm sure most of you are kind of bored right now, unless you're big psychophysics nerds, in which case you're my people. But what we were able to do so that no one has to go through this tedious stuff anymore is we took these data and we created a model, like the simplest model we could think of, to try to predict how detectable or discriminable a stimulus an electrical stimulus would be. So the way we did it is we created this volume of integrated fire neurons. They're not even connected together. That's how simple this network is, or this model is. Then we can sort of model an electrode in this volume. We know that the proportion of firing, this is an empirical result, decreases as a function of the distance. So this is an empirical function of probability of firing as a function as a function of distance from the tip for electrical stimulation. We pass the population response through an integration time window, and then we do an ideal observer analysis on the resulting. So we simulate the neural response evoked by a given stimulus, and then we use ideal observer analysis to determine how detectable or discriminable stimuli would be. The details don't matter. Here's the take-home message. We can predict with 96% accuracy how detectable or discriminable, a pulse train will be, or how discriminable two pulse trains will be using this very simple model that just, it's almost laughably simplistic. But it does what we need it to do, and this is, published in the journal Neural Engineering. This is not a science result, this is a neural engineering result, where we can actually, now, people doing this kind of work don't have to do this tedious stuff. They can use our simple model that has like a dozen parameters. They can just implement it at home and figure out how detectable or discriminable stimuli will be. Okay. Now back to the sensory encoding algorithm. I told you DARPA doesn't really care about this stuff. They just want an algorithm. It's like, give me a set of numbers that maps input to output. How do we go about developing an algorithm from these data? Well, I told you we have our detection or discrimination curves based on mechanical stimulation of the skin. We did the exact same thing on the same monkeys with matched locations on the hand, in the brain, with electrical amplitude detection discrimination. And then we made the following assumption, that if something was 80% detectable or discriminable with mechanical stimulation of the skin, and 80% detectable or discriminable with electrical stimulation of the brain, they were perceptually equivalent. And then we could do that with with each level of detectability or discriminability, and we achieve these functions, which I call the psychometric equivalence functions, which map electrical on mechanical amplitude. This is exactly the kind of algorithm you want. Mechanical amplitude is sort of the output of your sensor. It's related to pressure. This is the amount of electrical stimulation that you want to pump into the brain. And basically, here, let's use PAPS as an example. This means that if you want to create a sensation that is equivalent to a 400 micron indentation of the skin, you need to electrically stimulate the brain with 60 microamps, right? So the idea is in time, you just take the output of the sensors, which tells you how much pressure is exerted, and this tells you how much to electrically stimulate the brain to create an appropriate sensation, so that if it's a little bit of pressure, you'll get a weak sensation. If it's a lot of pressure, you'll get a strong sensation. So there's a little bit of variability. So each of these lines corresponds to a different electrode. Each of these colors corresponds to an animal. But there's a little bit of variation there, but really the shape is always the same. It's like a sort of power function with an exponent less than 1. Okay, so we got these functions. There's a lot of stuff that just happened in the last 5 or 10 minutes in this talk. Maybe I lost half of you. It doesn't matter, because I'm going to show you, this is a proof of the pudding, is a part of the talk, where we took our algorithm and we tested it, okay? And we tested it in a prosthesis with a monkey, right? So here we had the monkey do this pressure discrimination task that I showed you earlier. Except instead of feeling the stimulus on their skin, we delivered the exact same stimulus using the exact same stimulator on the prosthetic finger, and took the output of the pressure sensor on this prosthesis, in real time converted it to a pattern of electrical stimulation to the brain, quasi-real time, to the brain, so that, so this is a low pressure stimulus evoking a lower electrical stimulation. This is a stronger pressure evoking stronger stimulation of the brain. And the animal had to do this pressure discrimination task based on information through this neural interface. This is the figure that shows you that, so these are different levels of indentation, and these are the output of the pressure sensor, just to show you that I've been using amplitude as a proxy for pressure, and this shows you that it's a good proxy for pressure, and that you increase indentation depth, you get greater pressure. And then and accordingly, you get greater electrical stimulation of the brain. So then we compared the performance of the animals when they were doing this pressure discrimination task through this brain interface to their performance when they were actually feeling the thing. And the purple trace shows the performance on the pressure discrimination task when the animal felt the stimulus. The magenta traces show the animal's performance when they were doing the same task, but through the brain interface, and you can see that they were doing for 2 different electrodes, and you can see that the animal was just as good in that case, right? Validating our psychometric equivalence function that claimed that that's exactly what we had achieved, right? And by the way, I could have made the animals better. I could have just turned up the gain, and boom, they are way better than we are, or than they are with their skin, with this prosthesis. The issue with that is that you have a limited range of electrical stimuli that you can apply to the brain before you start burning holes into it. So this allows us to really extend the dynamic range of the sensations, make them sort of commensurate with the sensations that we experience in everyday life, and hopefully make these signals more interpretable to the motor sort of planning parts of the brain. By the way, this was a cool result too. Just this one time, for a single day, because we didn't want the animal to learn anything, we had the animal compare a standard stimulus of 440 microns, so almost half a millimeter indentation, which we had determined using our psychometric equivalence function to be perceptually equivalent to 50 microamps. And then we paired this mechanical stimulus with electrical stimuli ranging in amplitude from 20 to 80. And all the stimuli that were the electrical stimuli that were less than 50 microamps were perceived as being less intense than this mechanical stimulus, and vice versa for those more intense than 50 microamps. Just again, validating our function, and also showing that these mechanical and electrical stimuli are on a continuum, on a common intensive continuum, right? Because they were able to do that immediately. They had never done that before. Compare mechanical and electrical on the intensive continuum. Okay, so this is all our animal experiments. We sent all this stuff to the FDA, along with some super boring stuff where we chronically implanted electrode arrays and chronically stimulated for 6 months to make sure that we weren't burning holes in the brain or damaging the electrodes. And we found and showed that we didn't. And so the FDA approved human trials of this electrical stimulation. And this was done at the University of Pittsburgh by my colleagues, led by Rob Gaunt, Mike Boninger, Andy Schwartz, and Jen Collinger. So, before I get into that, the idea though, our animals are completely intact, right? So we can map out where the electrodes go, and we can do some certain things that we can't do with the tetraplegic patient. On the other hand, though, human tetraplegic patients might be paralyzed and insensate from the neck down, but they can talk. So the idea is to do these mappings, we electrically stimulate through an electrode, let's say electrode 35. We've shown with our monkey work that stimulating electrode 35 will produce a very highly spatially localized sensation, let's say on the index fingertip. So now we can connect the sensor on the index fingertip, the prosthetic index fingertip, to electrode 35. Anytime the sensor touches something, you electrically stimulate through electrode 35. It'll produce a sensation on the index that will be, and therefore kind of convey information of where the contact happened with the prosthesis in a sort of intuitive way. And how much to stimulate through electrode 35, we have our mapping that says, given this amount of pressure, this is how much to stimulate to give an appropriate percept. Okay, so, oh shoot, I forgot there's sound on this. I'm gonna have to describe what's going on because there's no time to try to fix this. Can you hear this at all? Okay, what's happening is this is Nathan, another patient who is tetraplegic also, but who has now 2 arrays of electrodes. One of it is motor parts of the brain, like Jan that I showed you earlier, and one of the somatosensory parts of the brain, where we could deploy the algorithms that we've discussed. And in this test, basically, Nathan is blindfolded, and Rob Gaunt here is touching different fingers. They've done this mapping that I just described, and Nathan actually perceives anytime Rob touches his index finger, Nathan reports a sensation on his index. So this mapping that we found in the monkeys extends to humans. We also did a little bit, because we didn't have to do a bunch, we did a little bit of psychometrics on the human patients, detection threshold, discrimination thresholds, and found that really the sensitivity to ICMS, intracortical microstimulation, in humans is very similar to its monkey counterpart. And so all these models that we developed for monkeys can be applied just rote in humans, right? So you don't have to go through this tedious work. And in monkeys, you can just get them to do this task over and over again for month after month after month after month. But in a human tetraplegic patient, they already have enough problems in their life that they're not going to do this extremely boring thing on top of that. So this really kind of allows, every time we submit a grant now, we have to spend like a page to explain why it's important to do monkey work, because there's a lot of stuff you can't do in the humans. So this is all well and good, but really in the end, I started this whole talk, well, one of the things I said early on in this talk was we're doing this to make people better using these prosthetic hands, right? And it does. So this is work showing Nathan doing this task, moving things around with and without touch. With and without the sensory feedback. Because the nice thing here is you can turn it off and see how good or bad he is. And you could probably see just from this movie that he's way better. Because he knows, if I'm grasping this object, I don't even know when these fingers touch it, right? I just have to take it on faith that they're touching, and you sort of, whereas the instant he touches it and has this tactile feedback, just to give you a sort of intuitive feeling of why he's better here, the minute he touches something, he knows he's made contact with it and he can start moving it. Here, just let me finish. I'm like 1 slide away from finishing. And this is just a quantification. It takes him longer without touch than with touch. And if you use, this is a clinical sort of assessment of limb function, and you can see there's a significant improvement with touch than without touch on this clinical assessment. And this is just to show that progress marches on. This is Jan doing this task. This is without touch. And this is Nathan doing this task with touch, even with 4 fingers, because the middle finger is messed up. And it's obvious that Nathan is better. So what's happening here is not only are you incorporating touch, but you're also improving your decoding algorithms. And this starts to look pretty fluid on the right. So these are the people that did the work. Terry has been collecting gobs of data, as did Greg. And then these are my engineers who got all this working. And Greg and Sunshin have been really instrumental in analyzing the behavioral data. This is a big consortium of people who worked on this called Revolutionizing Prosthetics. The main players that are relevant to me are the group at Pitt that I mentioned earlier. And this whole Revolutionizing Prosthetics was run out of the Applied Physics Lab. The PI was Mike McLaughlin. And then my handler or whatnot was Francesco Tenor. And these are my my funding sources, and most of this work was funded by DARPA. Thank you for your attention.
So when you do or don't have the stimulation feedback,
Yes.
Can you infer that people are using different strategies? I mean, you've looked at it way more than I have, but it looked like with stimulation, they were willing to presumably they feel it when that happens.
Yes.
So maybe like the open loop part of it, you can tell what people are doing.
This is pretty early days in terms of analyzing the kinematics. I don't think anyone has done that. But what people have done is ask them, why do you think you're doing better? And when they report, what he reports is, because this is the first guy who actually can control a robotic limb and feel through it, right? What he reports is that he just feels the instant he's made contact. So he has a much better sense of when contact is made. And so that's probably, if you don't have a better sense, then you go slowly, and then until you see the thing move or something. Because the visual system is ill-suited for this. It's too slow for this, right? The tactile system is right there, right next to the motor system to provide information. So, but nothing real deep has been done in that.
Okay. Simon?
Is there, is it just the binary sensation that I am in contact and not in contact that is sufficient for the improved performance, or are these tools spatially explicit, encoding, pressure sensitivity?
Excellent question. So here, I'll answer this in two parts. First of all, the binary thing is significantly better than nothing, right? The algorithms that are being used here are pretty primitive and not very good. So, because this is kind of old now, right? Now we're using different algorithms that I can get into if you're interested. The hypothesis, and the reason why I'm not talking about this yet is because I don't have any data to back it up, but the hypothesis that we're working from is that once you start, because what we're not using here is we're basically tracking pressure on the prosthesis. That is not at all what the brain does. I sort of mentioned this earlier to you. What the brain does is has these massive transit of the onset and offset of contact, and very little signal during maintained grasp, right? So now we're starting to build that into it, right? And here's the real problem, and we've done that, right? The real problem, though, and by the way, this is done roughly, in broad strokes, by creating algorithms that are not tracking pressure, they're tracking changes in pressure, right? Mostly changes in pressure and a little bit of pressure, because you do get a continuous signal, but it's a much weaker one. The issue, though, is that these robots are not very good. The sensors are not very good. And now we're getting at the point where the bottleneck is no longer the touch part, it's the robotics, and it's the sensorization. The sensorization drives me nuts, because I told them, this is the kind of parameter we need for the sensors, and they made this crap sensor that is completely inadequate, even though other people had much better sensors. I hope no one from IKEA is watching. Anyways, so those are the problems that are now being fixed, is how to, in order to demonstrate an advantage beyond what we have now, we need to improve on the robotics, on the sensorization, and that's what I think is next.
Can I ask a quick follow-up? So
Sure.
So maybe the other question then is, really impressive on the prosthetics and on what maybe is quintessentially the engineering side. What are the big science questions on the representation side
Right.
that you think are the next big things?
Right, so-
the sensors that we have available.
Great question. So I think I was going to say that and I forgot to. The experiment that you would like to see, I think, is if we, for instance, scrambled the finger feedback, would that have a significant effect on the performance? The problem is, you can't really do that with the tetraplegic patient. You can't just make things deliberately bad and then show that they fumble with it. So I think those are the kinds of experiments that we're fixing to do in monkeys, where we kind of tweak the sensory feedback and then see what are the keys to make it useful versus not. But that hasn't been done.
Let's see if we can get the next question back here.
Great work. Good question.
Sure.
So you try to leverage the natural mapping
Yes.
of the cortex, and so how might natural cortical remapping after an injury and the whole timeline of intervention and application of your device might affect that? And secondly, also, how might neuropathy or damaged nerve pain interfere with your signals?
Right. I can definitely answer the first question. I don't know about the second. I'll do my best on the second. So for the first question, right? So this is a great question, and it's one that we really struggled with until I met this professor at Oxford who works on amputees, and then educated me a little bit. And this is actually the paper that I was referring to in Transom Cognitive Science. It was written by Tamar Macon, who was at Oxford, now at UCL. So here's the result I think that you're alluding to. If you amputate, I mean, if someone gets amputated, that part of the brain that used to respond to the arm now can be activated through typically face or some other body part, right? And so that has been, I think, mistakenly interpreted as, whoa, look at this amazing plasticity in the brain, right? And again, there's a whole paper about it I could talk about until I was blue in the face. I'll just say a few things about it. One, just look at the prosthetic stuff. If you take an amputee, for instance, and you put an array of electrodes in his or her peripheral nerve, and this is an amputee that's been amputated for 20 years, right? So has not felt anything from their hand for 20 years, and you electrically stimulate this peripheral nerve, instantaneously the hand pops right back. That implies that pathway that was going from the hand to the brain is there, dormant, waiting to be activated again. In the somatosensory cortical patients, so what happens initially, actually, there's a lot of spontaneous activity in somatosensory cortex. Basically, they have a lot of just phantom sensations all over their bodies. But once you start electrically stimulating the brain, after a couple of weeks, those disappear, and you have an idea of what the somatotopy is based on imagined fMRI scanning, imaging touch with fMRI. You can show that this hand representation, when stimulated, produces a sensation to the hand, right? All this so-called plasticity, I mean, it is plasticity, but all this so-called massive cortical reorganization, one, is caused by homeostatic plasticity in the brainstem. This beautiful work by Neeraj Jain in Bangalore on how all that stuff happens in the brainstem. And two, it makes sense because, because of homeostatic plasticity, you deafferent a large chunk of cortex, all the other connections are going to get stronger. But these are not the kinds of connections that do sensory computations and are involved in doing the kind of computation that you need for sensation. That's why in the end, I don't think we have to worry too much about it. And proof is in the pudding. This Nathan, it was 10 years after his injury that this happened, and some of the peripheral, some of the amputees with peripheral nerve interfaces were amputated for 20 years, and boom, that pathway is right there.
Let's try to squeeze in one more.
Do you see evidence that the open loop control gets better with just exposure to the stimulation after you turn it on?
That is a great question. Unfortunately, with the tetraplegic patients, all this stuff is like all wired and you need a computer in the room and stuff. So we haven't been in a position where we can let them use it for day after day after day, right? In the peripheral nerve for the amputees, yes. They improve with this closed loop feedback when they can take it home, and they improve more with the closed loop feedback than without it. But we need to be able to do that with the tetraplegic system. My hunch is that yes.
Okay, with recognition that the plasticity probably occurs more in the spinal cord than the brainstem, I'd like to take this opportunity to thank our speakers.